All right, problem 467. Calculate the percent composition. Do you remember what percent composition means?
Is that like for H2O, for example, you have three things, 2 hydrogens, 1 oxygen, 33% oxygen, 66% hydrogen?
No, that's not percent composition. Percent composition is not, because what you did just now is you said the molar ratio, 2 moles of hydrogen to 1 mole of oxygen. But percent composition is always percent by mass. Percent by mass.
Oh, yeah, I remember that. Okay.
So if we look at our first example, sodium hydrogen phosphate, right? The sodium hydrogen phosphate, sodium dihydrogen phosphate. Do you know what that compound or that chemical formula is?
I have my chart here. Let's see. H2PO4.
Very good. NaH2PO4. All right. So then, what's the molar mass?
You have to add up 1 sodium, 2 hydrogens, a phosphorus, and 4 oxygens.
Or you can just ask your phone, right? Because I think we're to that point now. As long as you're comfortable how to find it when you aren't given it. What's the molar mass of sodium dihydrogen phosphate?
The molar mass of monosodium phosphate is 119.98 grams per mole.
119.98. Now you always have to double check to make sure it's the correct formula. But 119.98, that's how many grams there are per mole. And you get that again by adding 1 sodium, 2 hydrogens, 1 phosphorus, 4 oxygens. So, from the periodic table, right? The masses.
Yeah, I got that. So now to get the percent sodium, you just take the sodium's contribution.
Which was what? How much did sodium contribute?
Do you have the periodic table there? Yeah, okay, so sodium is 23.
Very good. So what do we do with that 23?
23 divided by the 119.98 times 100.
Very good. And for the hydrogen?
That's 2, so 2 divided by the 119.98.
2, because there's each hydrogen is 1 and there's 2 of them, right?
That's right. And for the phosphorus, do you have the periodic table?
Let me get the periodic table here.
30.97, so about 31.
Very good. 31 divided by the 119, that would be our percent phosphorus, the mass percent of phosphorus in there. And then what for oxygen?
Oxygen 16. 16 times 2 is 32 times 4, 64.
That's right, 64 divided by this 119.98. Very good. So here's ammonium dihydrogen phosphate. What's the molar mass of ammonium dihydrogen phosphate? Double check and make sure.
The molar mass of ammonium dihydrogen phosphate is 115.03 grams per mole.
Grams per mole. Then what?
1 nitrogen, so that's 14 divided by that.
Very good. 14 divided by that times 100 to give us percent nitrogen.
4, 5, 6 hydrogen. 6 hydrogen. So 6 divided by that.
Very good. Times 100.
Phosphorus, did we say was 31 divided by that times 100, and then oxygen again, 32 divided by that times 100.
Very good. So this is the molar mass for ammonium dihydrogen phosphate. Okay, very good. How about this compound here?
CH32CO. I don't know what the name of that compound is.
That's all right. That's an organic compound that we haven't been introduced to, but we can still find its percent composition, right?
I guess so. So it's, how many carbons there?
That's a good question. What do you see?
I got 3, I think.
Yeah, that's right. 3 carbons. So we'll find the molar mass here because we don't know the name of it, right? So 3 times 12, that's the contribution of the carbon. And you know, you can always kind of do this individually because then it's going to be helpful for later on, taking that 36 dividing by the total, right?
Okay, yeah.
So how many hydrogens?
6.
So 6 times the 1 for the hydrogen, and then 1 times the 16 for the oxygen, right? Okay, 6, 16. So 36, 46, 58. So it looks like the molar mass here is 58 grams per mole. And I think that that chemical is actually called acetone, right? Chemical formula for acetone. We really don't know what the chemical is there because we can't say. See.
The formula for acetone is C3H6O.
Whoops, I meant the molar mass. And it says there 58.06. We really don't know just by the chemical that's provided, but I do know that acetone has that same chemical formula. So that's one way of knowing it. Chemical structure for acetone is like this. You have a carbon double bonded to that oxygen, and then 2 carbons down below here with 3 hydrogens on them, right? Let me draw that out one more time for you. See, with our hydrogens coming off this time, right? And there's some organic chemistry, so you don't need to think about that, but it'll be a little more familiar to you when you come around the next time. All right, so if I wanted to know the percent carbon, what would I do?
36 divided by 58 times 100.
Very good. And then for hydrogen, 6 divided by 58 times 100, and then for oxygen, 16. Excellent. Calcium sulfate dihydrate. What's the chemical formula, Fred?
Calcium Ca. Sulfate, let me look at my thing. Oh, it's SO4 2 minus. So, calcium, so, wait a second. Is that calcium sulfate dihydrate right there?
That is. Very good. Calcium sulfate dihydrate right there. CaSO4 2H2O. That's interesting that they have 2 like that, huh?
Yeah.
Well, they might have been testing us, but it also might be a mistake in the book. There are a handful of mistakes in the book, so don't be too surprised when you see them, right?
Okay, so what's the molar mass?
Molar mass of calcium sulfate dihydrate.
172.172 grams per mole, according to some information I found on Wikipedia.
Yeah, so I'm just double checking, making sure that they got the hydrates in there. Okay, very good. 172.172. All right, so calcium. What's calcium's mass?
Is it 40?
Let's bring it in here and see. Yep, looks like it's 40.
So 40 divided by the 172 times 100?
That's right. Sulfur?
Is that 32.35?
32.0.
32.0.
Okay, so 32.0 divided by that 172?
Yep. Oxygen, you got, let's see, how many? 4 on the calcium, 5, 6. So 6 times 16. What's that?
Let's see, 6 times 16. Where's my calculator at? Yeah. Where's my calculator? Here it is. Okay. So 6 times 16, is that 72? 96. 96. 96. Okay. So what do we do with the 96?
Oh, that's the mass of the oxygen. So just 96 divided by that times 100.
Very good. Did we do hydrogens?
I think so. 4.
4 divided by 172.172.
Yeah.
Okay. Excellent job. That's 467. All right. Which has a higher percentage of oxygen? Morphine or heroin?
Oh, it looks like heroin.
Oh, that was fast. How did you know?
Oh, because there's 5 oxygens and there's only 3 in the morphine.
All right. Well, should we double check? Because, I mean, doesn't the amount of mass of the other components change the percentage overall because of the change in mass?
Oh, yeah, I guess so.
So C17H19NO3, we could find that mass. 17 times 12, 1 times 19, plus 14, plus 46, right? For 3 oxygens. Okay. Let me see if the computer, if the phone knows this one. Molar mass of morphine.
The molar mass of morphine is 285.34 grams per mole.
Can you double check that, Fred?
Yeah, okay.
I'll also look for, while you're doing that, The molar mass of heroin. Molar mass of heroin.
The molar mass of heroin is 369.42 grams per mole.
Okay. So, is that right for morphine? Was this one morphine?
Yeah, that's right.
Okay, you did it?
Yeah, I got the same thing.
Okay, very good. So, now how do we find the contribution of, what are we looking for? Oxygen?
16, 16, 32 plus another 16 is 46, right?
That's right. So we got 46 grams of oxygen contributing. So divide that times 100 there. And here we got what?
Let's see, that's 46 plus 32.
Very good. So 78. Is that right?
I think so. Let me double check. I'm getting 80.
Oh, 80. All right. So 80 grams of oxygen. All right. So then, let's see which one has the most here. Let's get a little light on here for our calculator a little bit. Scoot this over a little bit. There we go. So we got 46 divided by our 285.34. That is 16% oxygen. Whereas the heroin, 80 divided by the 369.42 times 100. So you were right. The 5 there did make the difference. So the heroin has a higher concentration of oxygen. Okay, good job. All right. Have you heard of Freon before?
I think so. I had to put some in my... I thought that's what I put in the car. Is that right?
Okay, Freon, yeah. It's one of the... It can be a coolant in your car. It's also used as a propellant, or used to be used, right? It has a high percentage of chlorine and fluorine as well. And for that reason, it has... we've tried to reduce its use because as it's released into the atmosphere, it combines with or interacts with ozone in the ozone layer, and it breaks down the ozone. So we need that ozone layer to protect the Earth in those regions around the ozone hole down south, right, on the South Pole. So we've made laws to restrict the use of what we call chlorofluorocarbons, or chlorofluorocarbons, carbonaceous compounds that contain lots of chlorine or fluorine. So which has a higher percentage of chlorine? CCl2 or Freon, C2H3, Cl2F. Want to make a guess?
I think that the first one would probably have to have it, Freon 12.
Why do you think that one?
Because you got 2 chlorines and 2 fluorines, but only 1 carbon. On the other one, you got 2 chlorines. You only have 1 fluorine, but you got 2 carbons and 3 hydrogens. So maybe so.
Okay, let's take a look. Carbon on the first one, so that's 12 for Freon 12. We're looking at the molar mass for Freon 12. 12 plus 35. We'll do 35 for chlorine. It's 35.45, I think. And, that's kind of a critical one to make sure you kind of get the right number because it is kind of a half there. So 35.45, but that's times 2 because there's 2 chlorines. And the fluorine is 19. So 19, and that's also times 2. All right, so that's Freon 12. Molar mass of Freon 12. Let's see if the calculator got it for us.
The molar mass of dichlorodifluoromethane is 120.91 grams per mole.
Okay, 120.91. Now, Freon 141B, we got 2 of these 12s. We got the contribution by the chlorine again is 35.45 times 2. We got the contribution of the fluorine is only 19 this time, and then this time there's 3 hydrogens. Okay, so yeah, let's see. molar mass of Freon 141b.
260.209 grams per mole,
That's
according to
not
some
it.
information I found on ChemBK.
That's not right. So let's see here. 24, 35.45 times 2. That's basically 71. 21. So 24 plus 21, 45 plus 71. 116. You want to back me up there, Fred? Find out if I got the right value. That was kind of fast.
Okay. Yeah, I get that.
All right. Well, then we didn't suspect this, did we? Because we said that we thought that the bottom or the top one would have the higher percentage, but because the top one has a higher mass, why does it have a higher mass?
Because you're trading in a carbon on the bottom for a fluorine. You have a carbon, which is 12, and 3 hydrogens, 13, 14, 15, for a fluorine, which is 19.
Oh, you're right. Very good. So the bottom one is going to have a higher percentage of chlorine.
Yeah.
Okay, good job. So again, we would take our contribution by the fluorine, which is by the chlorine, 71, and divide it by each of these, right? Both of them contribute 71. Good. All right, so we got a compound here that contains 2.35 grams of phosphorus, and chlorine contained 0.539 grams of phosphorus. Found that 200 grams of compound of phosphorus and chlorine contain that much grams of phosphorus. So the difference is going to be the grams of mass of chlorine, right?
What do you mean?
2.35 was the total mass, right? So here's my pile of material. I got 2.35 grams of it, and I found out here that 0.539 grams is of phosphorus.
Oh, okay. And it says it's just phosphorus and chlorine.
That's right. So that means that 2.35 minus 0.539 is our contribution of the chlorine. Minus 0.539. So we got 1.811 grams of chlorine. And we want to know the percentage by mass of both.
Well, you just take the phosphorus mass divided by the mass of the sample.
That's right. And then do what?
Times it by 100.
And then the same thing with the chlorine. Chlorine mass over this divided by 100. Is that right?
Yeah.
Okay. Very good. Excellent job. All right. Here it is. Another drug, angel dust. A sample suspected of being this illicit drug was found to have a percentage composition of these amounts. Do these acceptably match the theoretical data? All right. So somebody found some chemical on a person, and they say, this is drugs. And they know it's not drugs. It's this other chemical that I use for whatever. And so they can determine whether it actually is the angel dust, the chemical that they think, by looking at the percent mass of the different compounds. And once they found it was 84.71% carbon, 10.42% hydrogen, and 5.61% nitrogen, they then can use that to compare. So basically what we want to know is, what is the percent carbon in angel's dust? Well, do you think that the phone knows what angel's dust is?
I doubt it.
What's the molar mass of angel dust?
The molar mass of phencyclidine is 243.39 grams per mole.
It did.
That's right, it did. 2.43.39 grams per mole. So what percentage is how do we determine what percentage is carbon?
12 times the 17 divided by that number.
That's right. So what's 12 times 17?
It's 204. 204.
Very good, 204. So 204 divided by 243.39. 243 83.39 times 100. So we're looking at 84%. Well, it's actually a little bit low, 83.8%. That's 84.71. What do you think?
Well, if you 12 is pretty close.
It is pretty close. Let's look at the periodic table. Right? You're saying that the mass of carbon is pretty much close to 12?
Yeah.
Well, we got 12.011. Let's try that. 12.011 times our 17 this time. And that gives me 204.187. Now if I divide that by my 243.39, that time I get 83.89, and that's 84.71. So there's a slight discrepancy.
Well, let's try the hydrogen.
Okay. 25. Maybe I should get a little bit better. 1.0079 times 14. No, 25. Times 25. 25 hydrogens. And then I'm going to divide that by my 243.39.
10.35%?
Second one that's kind of off a little bit.
Yeah.
So let's try the nitrogen. 14 divided by my 243.39. Is there just one nitrogen?
Yeah.
Okay. So 5.75%. Yeah, so what would we say?
The guy didn't do it.
What do you mean?
Well, the person you caught didn't do it.
It might have been a girl.
Oh, yeah, but they're probably not carrying the angel's dust.
That's right. Very good. So it doesn't look like our data match up very well. All right. Good job. How about this one? How many grams of oxygen are combined with that many atoms of nitrogen in a compound of dinitrogen pentoxide?
I think this is best with an equal sign.
Okay, so what do I put to the right of my equal sign?
You want grams of oxygen.
Very good. And what do I start with?
You can start with 7.14 times 10 to the 21 atoms of nitrogen.
Very good. 7.14 times 10 to the 21 atoms of nitrogen.
Yep, and then you can go from atoms to moles.
How do you go from atoms to moles?
It's Avogadro's number.
Do you remember it?
I can't really.
Okay, so we can always ask, what's Avogadro's number?
The answer is 602 sextillion, 214 quintillion, 85 quadrillion, 700 trillion.
Or in other words, 6.02 times 10 to the 23rd, it says right here for me. Okay? Right? So that's how many what?
It's how many atoms are in a mole.
Well, it's how many atoms are in a mole of atoms. It's also how many dogs there are in a mole of dogs, right? It's the mole. Got it?
Yeah, okay.
All right, so 1 mole of nitrogen. Now, why is that going to be helpful?
I'm not sure. Why did we go to moles?
Well, we went to moles because then we could take advantage of the power of the stoichiometry, right? Dinitrogen pentoxide, what's that chemical formula mean?
Oh, N2O5?
That's right, N2O5. So from this stoichiometry, I know that there's a relationship between the moles of nitrogen and moles of oxygen. And once I get moles of oxygen, I can go to grams of oxygen. Right?
Okay, so let's see, 2 to 5.
2 to 5 is what?
2 nitrogen moles to 5 oxygen moles.
Okay, very good. And what's this number here?
That's 16 grams per mole.
16 grams for every mole. All right, so there's our number divided by our Avogadro's number times 5 divided by 2 times 16 should be our answer. Okay, good. Okay, so here we are, empirical formulas. Do you know what the empirical formula for these compounds is?
What's the empirical formula again?
It's the simplest whole number ratio of atoms of a molecular formula, right? So this is going to be for a molecule, right? We're talking about molecules. And molecules, when you identify their chemical composition, what you'll get is what we call the empirical formula, which is the simplest whole number ratio. You don't know if that's how they are molecularly. You just know that the ratio of atoms are those values. And so that's what we call the empirical formula. So you take these these formulas, which are molecular formulas, S2, S2Cl2, and we're going to try to find out what the empirical formula is.
So is it just SCl?
That's right, for A. And B?
CH2O?
Good. C?
And I don't know. Can you do anything to C?
No, you can't. That's right. So if that was the molecular formula, it's also the empirical formula. Okay, good. How about D?
ASO3?
Very good. And this one?
HO? Is that water? No, what's going on there?
That's hydrogen peroxide, right? H2O2.
Oh, yeah, I remember that. Okay.
So HO is the empirical formula for hydrogen peroxide. Good. All right, here we go. Sample of sodium pertechnate had a mass of 0.896 grams, found 0.11 grams of sodium and 0.477 grams of technetium. The remainder was oxygen, and we want to know the empirical formula for sodium pertechnetate, used for brain scanning agent in medicine. All right, so what's the chemical formula?
Well, it's got some sodium, some technetium. What's the chemical formula for technetium?
You mean the elemental symbol?
Yeah.
TC? Should we look it up here, make sure we can find it?
Where is it at?
It is down... Where is it at? Technetium. There it is, right there.
It is TC.
Yep. All right, so we got some sodium. We got some technetium. And we got some oxygen, apparently, right?
Yep.
So, how many grams of sodium?
0.111.
0.111 grams of sodium.
And 0.477 grams of technetium.
0.477 grams.
And then, to get the oxygen, can you just take the mass of the sample and subtract those two?
That's right. Good. So we got 0.896 minus the 0.111 minus the 0.477, 0.308. So that's how many grams of what?
Oxygen.
Very good. How do I find the empirical formula from that?
Can you just take the Na.111?
Like this?
Yeah, and then TC 0.477, and then oxygen 0.308, yeah, and then divide by the smallest, which is 0.111.
Well, not quite. What's wrong with that?
Oh, yeah. No, sorry. Never mind. Just erase that.
What was wrong with that?
Well, you can't do that because those are grams, and the XYZ there, that's in moles, yeah.
Okay, very good. But we know now that we just have to convert these to moles of nitrogen, right? Or sodium. Moles of technetium and moles of oxygen, right?
Yeah, so there's 23 grams per mole for sodium.
23 grams, 1 mole, right? 20 grams goes on the bottom because we need grams to cancel out.
Technetium, what was the molar mass of that one? 95, is that what that says?
Want to help me out, Fred?
Yeah, I'll get it.
Oh.
$98.9.
Very good. 98.9 grams per mole. And then 16 grams of oxygen for every 1 mole of oxygen. All right, so what do we got?
Can you use your phone?
That's a good question. Well, should we try it? How many moles of sodium are in 0.111 grams of sodium? No luck. So, got to use the calculator. 0.111 divided by 23. 0.0482. 0.477 divided by our 98.9. 0.00482. That's nice. Wait. Oh, I forgot a zero on that one there. So those are the same masses, or same molar ratio. And then the last one.
0.308
Oh, yeah, 0.308
divided by 16.
divided by 16. 0.01925. Okay, does that make sense?
Well, it's the right value.
Okay, so then what are we going to do?
Well, now you can take those values and put them on the sodium and the technetium and the oxygen.
Very good. This is moles of technetium, and this is moles of oxygen. So sodium 0.00482, technetium 0.00482, and then oxygen 0.01925.
Then divide them all by the 0.0428.
Very good. This is going to be 1 sodium, 1 technetium, and then what's the other one?
It's going to be like 4, I think, right?
Let's see. How do you know?
I don't know.
0.01925 divided by 0.00482. Oh, you're right. It is 4. How did you know?
I think I did this one before.
Okay, very good. So there's our empirical formula. Hey, what kind of compound is this? Molecular or ionic?
How can? Oh yeah, it has a metal, so ionic.
That's right. It's an ionic compound. What is the charge on these ions then in that ionic compound?
Sodium's +1.
Very good.
So that means the TCO4 must be a -1.
Very good. Excellent job. Okay, let's try to find the empirical formula for this compound given the percentages now. Okay? So what do you think we do?
14.5%. I don't know. What do we do?
Well, we hopefully remember that percentages is always given in terms of mass percent. So then we can talk about a 100-gram sample and say that 100 grams of a sample will be 14.5 grams of carbon and 85.5 grams of chlorine. So from that 14.5 grams of carbon, we can convert that to what? What do we want?
Moles?
Yeah, how did you know to go to moles?
Just guessed.
Well, the way that we know that we want to go to moles is because the empirical formula is a molar expression of molar relationship between the different elements, right? So again, this is some sort of CXCLY compound. We don't know X and Y are, but X and Y are expressing a molar relationship, the moles of carbon to moles of chlorine. So if we know how many grams of carbon, we can convert that to moles of carbon, right? 12 grams for every mole. And then we can do the same thing and get moles of chlorine. From that percentage, again, we're just treating it as grams because we're assuming we have a 100-gram sample, right? 35.45 grams of chlorine. Can you double check on that? Is that the molar mass of chlorine?
Yeah, that's right.
Okay, so now we go 14.5 divided by the 12. There's our 1.208 moles. And then 85.5 divided by 35.45. And so that's 2.41 moles of chlorine. All right, so then what?
Those for the X and Y, right?
That's right. So C 1.208, Cl 2.41.
But then you divide them both by the smallest, 1.208.
That's right. And if we do that, that's going to set one of them to 1 and the other one to what?
Oh, it's 4, right?
Yeah, it looks like, oh no, sorry, 2.
2, oh yeah.
Very good. So CCl2 is our chemical formula for this compound. Just, yeah. All right. Good. All right, next one here. Same thing. We got percentage of our compounds, carbon and hydrogen, and some oxygen. And now we want the empirical formula. So what's the generic empirical formula for this compound?
What do you mean?
Well, it has what?
Carbon, hydrogen, and oxygen?
Yep, and then what do we put down here?
Oh, I guess like X, Y, and Z.
Very good, X, Y, and Z. And now how are we going to get the moles, that's what this X, Y, and Z is, right, from 72.96%?
Well, you said that the 72.96% is in grams, so that if we had a 100-gram sample, it's like 72.96 grams of carbon.
That's right. So what would we do with that 72.96 grams of carbon?
Convert it to moles.
Why do we convert it to moles?
Because we want the molar ratio.
That's right. So 12 grams for every mole. Very good. And then that value there would be the value that you'd put here, correct?
Yeah.
And then for the 5.4 grams of hydrogen, we go 1 gram of hydrogen for every 1 mole of hydrogen. And then that would give us moles of hydrogen. Right?
Yeah, and then what do you do for oxygen?
Well, what do you think?
I guess we know that oxygen must be 100%, or the rest must be oxygen, right?
That's right. So if I take 100 and subtract the 72.96 and subtract the 5.4, right? Should that give me a percentage?
21.6%.
Very good, 21.64%. So what do I do with that?
Can that be grams too?
Yeah, I can just say I have, again, a 100-gram sample. So that's how many grams of oxygen there would be. 16 grams of oxygen for every 1 mole of oxygen. And that's going to be our moles of oxygen, right?
Yeah. Okay.
So 26.14 divided by 16, 1.63375. 72.96 divided by 12, 6.08. 5.4 divided by 1, 5.4. So we got C, 6, H, 5.4, and O, 1.63375. Now what?
Divide that all by the smallest, the 1.63375.
Very good. 6 divided by that smallest. That's 3.67. 5.4 divided by the smallest. 3.3. And 0.1. That doesn't look very good, does it?
Did we make a mistake?
We might have. So make sure we got 5.4 here. So 100 minus the 72.96. Did I do that right? Minus the 5.4. That's 21.6. Uh-oh, there's the problem right there. 21.64. What did I write? Well, there's the problem. 21.64. 21.64 divided by 16 is actually 1.35. Okay, so if I divide all of them by 1.35, then I got 3.67, no, 6, sorry, 6 here, divided by the 1.35. All right, that's 4.4. Still not very friendly number. H is what? 5.4 divided by the 1.35. H4, and then O would be 1. So maybe this is 4.5, and then we go up to C9, H8O2. Why don't we check the answer in the back of the book, see what we get.
Okay.
Okay, so here we are, back of the book, 485, C9H8O2. Okay, so that was it.
So we knew we had to go up to 9 because it was like almost 4.5?
That's right. That's right. So we're close there. And if we would have used 12.011, maybe we've been closer to 4.5. Okay, good. Okay, 487. We got an organic compound, contains only carbon, hydrogen, and oxygen. But this time, they haven't given us percent carbon, percent hydrogen, percent oxygen. What they told us was that they combusted it. Do you remember what combustion is?
Is that reacting with oxygen?
Very good. It's a fancy term for reacting with oxygen. And usually, you're talking about an organic compound. Do you remember what an organic compound is?
Means like fresh, right?
No. Organic compound refers to something that is mostly carbon or hydrogen. And anything else that's with that carbon or hydrogen is called a heteroatom. Hetero meaning different than carbon or hydrogen. So an organic compound is a compound that contains mostly carbon or hydrogen. And combustion is the combination of an organic compound with oxygen, and the products are going to be the carbon going with the oxygen to form carbon dioxide, the hydrogen going with the oxygen to form water. All right? If this organic compound has some sulfur in it or some nitrogen, then you'll also get SO2 or NO2 or SO3 or NO or SO, right? So other compound or other products where the other heteroatoms go with the oxygen. That's why when we burn gas, we got to make sure we're burning pure gas, not nitrogenated or sulfonated gas, because you'll get sulfur dioxide and nitrogen dioxide, right?
Oh, I didn't know that.
Yeah, and then sulfur dioxide in the air combines with the moisture and creates sulfuric acid. Nitrogen dioxide combines with the air and creates nitric acid, and that's where you get acid rain.
Oh.
Okay, so, wait, Fred, are you there?
Oh, I'm here, but my camera's not working.
Let's see what's going on.
Oh, there I am. Okay, thanks. Yeah, so acid rain, huh?
Yeah, that's right. So what we want to do then is from the combustion information, we want to compare, again, what's the ultimate thing we're after?
And the problem?
Yeah, what are we trying to find here?
Let's see. Empirical formula of the compound.
That's right. So we want X, Y, and Z. And what are X, Y, and Z?
Oh, that's the molar ratio?
That's right. X number of moles of carbon, Y number of moles of hydrogen, Z moles of oxygen. So we want the molar ratio for our elements, right? Okay. So how can we get that?
Well, if you had the grams of carbon, I could get it.
All right. We want moles of carbon. We know how to get it from grams of carbon. But what about grams of carbon dioxide? How can we get it then? Well, we want, again, moles of carbon. And we can get it because there is a molar relationship between the moles of carbon here and the moles of carbon there. All the moles of carbon here end up as the carbon dioxide. So if I can go from grams of carbon to moles of carbon, grams of carbon dioxide to moles of carbon dioxide, I can go from moles of carbon dioxide to moles of carbon here because it's the same number of moles, right? This isn't a balanced equation, so you might say there's only one carbon here and there's X here, but that would be fixed by the coefficients, balancing it. So essentially, we can go from moles of carbon dioxide right to moles of carbon. Okay? So grams of carbon dioxide to moles, moles of carbon dioxide to moles of carbon. And then that moles of carbon will tell us information about that X there. Okay, good. So, same thing can be done for moles of hydrogen, starting with grams of what?
Water?
That's right, grams of water. Because grams of water can do what?
Moles of water?
That's right. Why do we go to moles of water?
Because there's a relationship in the equation.
That's right. For every mole of water, I can tell how many moles of hydrogen there are.
Okay, good. So that's 0.805 grams of water.
Okay, 0.805. How about grams of carbon dioxide?
1.312.
Let's finish this one up here first.
For every mole of carbon dioxide is 44 grams.
Very good.
And there's, I can't remember that one. What's that one?
Well, how many moles of carbon are there for 1 mole of carbon dioxide?
Oh, that's just one. One carbon for every carbon dioxide.
That's right. Right? You can just look at the chemical formula and see there's 1 mole of carbon for every mole of carbon dioxide. How about this one?
Well, that's just one, too.
Are you sure?
Wait. Oh, H2O. So it's 2 moles of hydrogen for every mole of hot water.
Very good. Excellent. So 0.85. What about this one? We have to fill that in.
That's just the molar mass of water. So that's 18.
Very good. 18 grams of water for every mole. All right. So that value should give me moles of carbon. This information here should give me moles of hydrogen. Is that all we need?
Well, I think we need moles of oxygen, too.
That's right. We do need moles of oxygen. Where can we get that?
Grams of water, I'm not sure which one.
Well, the problem is here, the amount of oxygen that you add here doesn't end up here or there, or even it could end up on both, or some of these oxygens could have been this oxygen here, and we don't know how much oxygen we added here. And so we can't relate it as easily. But what we can do is we can take the moles of, or mass of sample, which is 0.684 grams. All right, so here's my mass of sample, 0.684 grams of sample. And from that mass of sample, I can subtract the grams of carbon, and I can subtract the grams of hydrogen, and what will be left over?
If the sample is made of carbon, hydrogen, and oxygen, right? Same chemical formula, right?
That's right, it's the CXHYOZ.
And you had grams of sample, and you subtract the carbon and hydrogen, all you'd have left was the grams of oxygen.
Very good. So that's how I can get grams of oxygen. And then from that grams of oxygen, I can get moles of oxygen for my chemical formula.
Okay, so that's 16 to 1.
What's that?
Grams of oxygen, 16.
Oh, yeah, okay, 16 to 1 there. Good. Now we got to find grams of carbon and grams of hydrogen. All right. Let's find out here. Moles of carbon, moles of hydrogen. Do we get an answer for these ones yet?
Let's see. 1.312 divided by 44.
All right, so I got 0.0298, 0.0298. How about for the bottom one here, moles of hydrogen?
0.805 divided by 18 times 2.
So that's 0.0894. Did you get that?
I think that's right.
Okay. So where do we get grams of carbon and grams of hydrogen from?
I'm not quite sure. Where can we get that? Well, why do we need that?
Well, because remember, grams of sample.
Oh, yeah. We've got to get the grams of oxygen.
Right. So where are we going to get grams of carbon and grams of hydrogen?
From the moles, we could go to grams.
That's good. That's right. So I know 0.298 moles of carbon, and I can convert that back to grams of carbon. Remember, there's 12 grams for every 1 mole. So that 0.0298, I multiply that by 12, and that gives me grams of carbon, 0.358. And then the same thing here, 0.0894. That one's just multiplied by 1 because this is moles of hydrogen going to moles of hydrogen for every gram of hydrogen, 1 gram of hydrogen for every 1 mole. So that's easy, 0.0894. So I got my 0.684, and I subtract my 0.357, and then I subtract my 0.0894. And the answer is 0.2378. Now, what is that?
That's grams of oxygen.
Very good. 0.23678. 68 grams of oxygen. So I divide that by 16, and that's going to give me moles of oxygen. 0.0148. There they are. What do I do with them?
That's your X, Y, and Z, right?
That's right. That's my X, Y, and Z. So I go 0.0148 on my oxygen. 0.0298 on my carbon. And hydrogen, 0.0894. Divide them all by what?
The smallest, 0.0148.
Very good. That's going to make oxygen 1. Hydrogen, I get 6. Carbon, 1.5. Whoops, 5. What do I do now?
The 1.5 needs to be multiplied by 2. So you got to multiply them all by 2.
That's right. We got to get this a whole number. So H12O2. There we go. That's going to be our empirical formula. See how we did that?
Yeah, I think so.
So the carbon dioxide told us the moles of carbon. The water told us the moles of hydrogen. The difference between the sample and the grams of carbon and grams of hydrogen could tell us the grams of oxygen, which we can convert to the moles of oxygen. Kind of confusing, but a powerful technique and very important to understand. Okay, next. All right, so next problem. Here we have a compound, organic compound. You remember what organic means, right?
Yeah, you just asked me last problem.
I know, but maybe somebody's here just for this problem.
Okay, it's something that contains carbon and hydrogen mostly, right?
That's right. It contains mostly carbon or hydrogen. And what do we call the atoms that aren't carbon and hydrogen in an organic compound?
Heteroatoms.
Very good. So we have this organic compound. We combust it. What does combustion mean?
Combine with oxygen to form carbon dioxide and water.
Very good. So we got carbon dioxide and water. It doesn't say anything about there being oxygen in this compound. It doesn't even say what the chemical formula for it doesn't even say if it has anything other than carbon or hydrogen. So we just assume that it's carbon and hydrogen. CXHY combined with oxygen. What are our products going to be?
Carbon dioxide and water.
Very good. Carbon dioxide and water. And from the grams of carbon dioxide, what can we learn?
Moles of carbon.
That's right, moles of carbon. Because grams of carbon dioxide goes to moles of carbon dioxide. And moles of carbon dioxide, all the moles of carbon from the carbon dioxide came from the moles of carbon over here. So this is a 1-to-1 ratio, 44 here for every 1 gram, 19.73. It can be grams or milligrams, right? We're talking about a 100-gram sample. So, no, sorry, we're talking about a 6.853 milligram sample. I'm going to, instead of saying milligrams, I'm just going to say grams. We can do that, right?
Oh, well, it says milligrams in the problem.
Yeah, but if I change this to grams, if I had a sample that was 6.853 grams and I combusted it, I would get 19.73 grams of carbon dioxide and 6.391 grams of water, right? So if I had 1,000 times more of this, I'd get 1,000 times more carbon dioxide and water. So I'm just going to use grams because then I can go right to moles. Otherwise, I just have an extra conversion factor here going from grams to milligrams. Does that make sense?
Okay, I guess you can do that.
Yeah, that's going to make it easier for me, more simple. So moles of hydrogen going from grams of water, 6.391, to moles of water, and then moles of water to moles of hydrogen. You remember what the ratio is here? Moles of hydrogen to moles of water?
Oh, that's 2-to-1.
Very good. 2-to-1. 6.391 divided by 18 times 2. Zero 0.711 no 0.710101 0.7101. There we go. And then this one 19.73 divided by 44 0.4484. Okay, very good. So now what do we do?
Divided by the 0.4484.
That's right. So we just have to divide them by the smallest one. So essentially what we've identified now is that we have C 0.4484 and H 0.7101. And then we're going to divide both these by the smallest one. Right? So it's C1H. What's that ratio?
I don't know.
Let's figure out. 1.58. That's a rough number. So when we get numbers that aren't exactly 1.5, I'm sure it's 1.5. So it would be C2H4. No, C2H3. C2H3. That's a weird empirical formula. But one thing that we can do is we can change this, get a little more accurate with our which one is it here? No, I think that all those should be fine. I guess we could double check, make sure we did it right. 19.73 divided by 44, 6.391 divided by 18 times 2. Okay, so I'm going to have to say that this is probably C2H3. I think that's one worth checking on because that's a weird chemical formula. Let's check it out on the back of the book. Well, looking at the back of the book, I'm going to tell you that this is not right. It was iffy. And the problem is they say, now maybe, did I take this? Let me double check here. Let me check one more thing. Maybe I didn't get the whole problem up here. Maybe there's more to the problem. That's the whole problem, but the thing that they don't tell us is that this compound contains oxygen. All right, so they needed to say that this compound contains oxygen. And the way that that will change things is we'll have an O with a Z. All right, we won't know what the mole number is, but from these moles of carbon and moles of hydrogen, we can get grams of hydrogen. That's 0.7101 grams of hydrogen. This one is our 0.4484 times 12. That is 5.38 grams of hydrogen, or grams of carbon. And then we can take, well, do you remember, Fred? What do you do?
Yeah, you got 6.853 milligrams of hormone, but you're saying grams, right?
That's right. We're using grams, so, you know, just everything, but we're multiplying it by 1,000. 6.853 grams of sample, right?
Yeah, then you can subtract your grams of carbon, 5.38. And your 0.7101
What is that?
grams of hydrogen.
0.7101 grams of hydrogen.
And then what's left over should be grams of oxygen, right?
Very good. So 6.853 minus the 5.3 minus the 0.7101. So I got 0.761. That's grams. Divide that by 16. 0.047 moles of oxygen. Now this time, we're going to divide all these by 0.047. And that's going to force our oxygen to 1. Hydrogen, 0.710. Divided by 0.047. that's 15. And then 0.4484 divided by 0.047, that's 9.5.
You got to multiply by 2, right?
Yeah, I guess so. We got it because we have that 0.5 there. So C18. No, 9 times 2 is 9 times 2 is 18. So this should be C19, right? C19 H30 O2. Is that right? There we got 9.5. 9 times 2 is 18, plus the 1 is 19. C19 H30 O2.
Okay, sounds good. Is that what the back of the book said?
Let's take a look. Yeah, there it is, 49, C19 H30 O2. Okay, good job. Okay, now we are good at getting the empirical formula, but now we want to be able to relate the empirical formula to the molecular formula. All right. So here's an example of a compound's molecular formula. C6H12O6, that's glucose. Can you tell me the empirical formula? If this is the molecular formula, can you tell me the empirical formula?
Divide them all by 6. CH2O?
That's right. So that's the simplest whole number ratio. That's the empirical formula. You can see also that there's a relationship between the empirical formula and the molecular formula, right?
What do you mean?
Well, if I take this one here and multiply by 6 times 6, right, that's how I get my molecular formula.
No, okay, I can see that.
If I took the mass of this compound, CH2O, and then took the mass of this compound, C6H12O6, that same multiplier would exist between those two masses. Because I'm multiplying this thing by 6, therefore it's like taking the masses and multiplying it by 6. So the same multiplier exists between what we call the empirical mass, that's just the mass of the empirical formula, and the molecular mass, which is the mass of the molecular formula. All right? So the empirical mass, we can just get by adding 1 carbon, 2 hydrogens, and 1 oxygen. And the molecular mass we can get by adding 6 carbons, 12 hydrogens, and 6 oxygens. So in a problems like these ones here, where they say here is the empirical formula, NaS2O3, and here is the molecular mass, all right, and they want to know the molecular formula. So they want the molecular formula. They give us the empirical formula, NaS2O3. And we don't know what the multiplier is here. Some number, some multiplier, times, not times x equals n, but just times n. But we do know that there's this relationship between the empirical mass and the molecular mass that also exists, which is also times n, some value. Now the empirical mass, we can find that by just looking at NaS2O3. 3 oxygens plus the 23 for the sodium. Do you remember what sulfur was?
Let me look. That's 32.
Very good. So 64 here. So we got the 3 oxygens, 48, 1 sodium, 23, 2 sulfurs, 64. 48 plus 23 plus 64. So I'm getting 135, and that is the mass for the empirical formula, which is the empirical mass. And they tell us that the molecular mass is 270.4, right? So from that relationship, we can take the 270 divided by 130, and it'll tell us what that n value is. What does it look like?
Oh, 2.
That's right, it's going to be 2. So then we use that here on the empirical formula and get Na2S4O6. You follow that?
Yeah, I got it.
Very good. So there's this relationship between the empirical formula and the molecular formula, And it's the same relationship between the empirical mass and the molecular mass. All right, let's try the next one. C2H3Cl. What's the molar mass of C3H2Cl?
12 times 3, 36, plus 2, 37, 38. So 38 plus, was it 35.45?
That's right. 35.45 is the chlorine. So I got 73.45.
I guess you multiply that by 2.
That's right. Or essentially what you were saying is you take the 147 and divide it by our 73.45, and we get our N value. Therefore, the molecular formula will be what?
C6H4Cl2.
That's right. Very good. How about the last one there? C2HCl?
That's 12 times 2, 24, plus the 35.45 plus 2.
So I'm getting 61.45. What do I do with that?
Take 181.4 and divide it by that 61.45.
All right, what's that tell us?
Well, the multiplier is 3, and the molecular formula is C6H3Cl3.
Okay, very good. Well done. All right, compound describing problem 489 was found to have a molecular mass of 290. What's its molecular formula? So 489, it's the sex hormone. That chemical formula was C19H30, no, not 18, 19, C19H30O2. And it was found to have a molecular mass of 290 grams per mole. So the molar mass is 290.8, or 290 grams per mole. And there's the chemical formula. What do we do?
I think you could find the empirical mass.
Very good. So we go 19 times 12. All right, we're trying to find the mass for this compound here. 19 times 12 plus 30 plus 16, 16, 32. So I'm getting 290. So the empirical mass is 290 grams per mole. The molecular mass is the same. What does that tell us?
The multiplier is 0? No, 1. Multiplier is 1. So, well, does that mean the empirical formula is the same as the molecular formula?
That's right. That does mean that. So we have 19 here. C19H30O2 is not just the empirical formula. It's also, in this case, the molecular formula. Okay, good.